So last time we discussed the so-called Mobius transformation. And it turns out that every linear, I should better say linear fractional transformation. So every linear fractional transformations maps lines and circles into another lines and circles. So every linear fractional transformation maps lines and circles to lines and circles. And today, we will be turning to some examples of very special types of linear fractional transformations. So what do you think is the most important object between, with that depends from person to person, but I believe the most important geometric object in the complex plane is upper half plane or a unicircle. So therefore, we will try to classify every linear transformation that maps a circle to circle or upper half plane to upper half plane or like upper half plane to another circle, like this. So the first example is so I want to classify a linear fractional transformation, a linear fractional transformation that that maps the upper half plane so this is our upper half plane. So that imaginary part of every complex number is greater than or equal to 0, then we say it's upper half plane. And suppose that I have this guy is mapping this upper half plane onto a unicircle. And it sends the boundary of the upper half plane to the boundary of the image of this guy. And then this is if and only if I times alpha and z minus z0 over z minus z bar of 0. So, therefore, every linear fractional transformation satisfying this property, then you must be able to write down your linear fractional transformation in this form. Oh, sorry, I forgot to mention this. Well, this guy, alpha, is a real number. So this is what sometimes we call this guy as a Cayley transformation. Okay. Before I prove the statement, therefore, so if you are convinced, then maybe you must be able to classify all such linear fractional transformation which maps the unicircle to upper half plane. So how would you get this? Well, just simply you invert this map, then you're going to get this. All right. Okay. So since this is an if and only if statement, so I'm going to give you the two-sided proof, and I will begin from this side. this direction first. Well, suppose that I have a linear fractional transformation. Suppose I have a linear fractional transformation, so AZ, B, and CZ plus D. Well, and of course, you must automatically consider that these four numbers, AD and BC minus BC, never be zero. Okay. Then in this case, we're going to consider three different points from the z-plane. When z equals to 0, when z equals to 1, and z equals to infinity. Oh. Okay. These 3 points, these 3 guys lies on the boundary of the upper half plane. And well, because of our assumption, all the images of all these 3 points must have the modulus 1, right? Then the image of z0 and z1 and z infinity. Yeah, I have intentionally chosen these 3 points because they are easiest to compute. So must have moduli 1. But well, I'm just consider. Well, first I will consider the image of these 2 guys when z equals to 0 and z equals to infinity. When z equals to 0, so therefore, if you plug in z equals to 0 into here and there, then which is just b over d, and since the boundary of this guy will be mapped to the boundary of this one, so this guy must have the modulus 1, and on the other hand, if you plug in the z equals to infinity, then what would then the function value at infinity is going to be just a over c, right? And so this number must be also 1. So B is D, and A is C. Okay. Okay. And what if I divide these 2 equations side on? Then B divided by A is D divided by C. Sorry. Yeah, I'll just. It is always okay to extend this absolute value, the top and bottom of this fraction. All right. Okay, so this is since this is our linear fractional transformation, and it turns out the modulus of ratios between these 2 leading term coefficient equals to 1. This gives us the idea. So I will just say z plus b over a and z plus d over a, right? Okay. Okay, and what is the modulus of this complex number? Well, because according to this, the modulus of this complex number must be 1. So since this guy has modulus 1, this implies you must be able to find another real number, say alpha, such that A over C is e to the I times alpha, right? And also, you must realize these 2 complex numbers, these 2 guys has the same moduli. So I'm going to set this guy to be Z 0 and this guy to be Z1. And Z0 and Z1, they have the same moduli. So eventually, I can simplify these linear fractional transformations like this, plus Z0 over Z plus Z1. Okay, now what? So, well, I already taken advantage of the modulus of the moduli of these two guys. This point equals to 1. So all I have is the last condition. Well, that is, if I plug in z equals to 1 into this expression, then the moduli of this fraction, complex fraction, should be 1, right? So, okay, so we're going to let z equals to 1. Then this is going to be e to the I times alpha and 1 plus z0 and 1 plus z1 and take a modulus and this guy has no effect on the modulus, so this is just 1 plus z0 over and 1 plus z1 and this guy equals to 1. So 1 plus z0 is 1 plus z1. So these two numbers have the same moduli. So therefore, so this equality is still true for even if I raise the power of 2. And so 1 plus z0 times its complex conjugate is 1 plus z1 times its own complex conjugate. But you know, when you take a complex conjugate, then this complex conjugate is only applied to these two complex numbers. And so 1 plus z0 plus z0 bar plus z0 squared and 1 plus z1 plus z1 bar plus z1 modulus squared. Okay, and these two numbers, they both cancel out each other. And on top of that, so since we know that these two complex numbers have the same moduli, therefore these two guys, they also cancel out. So I have this guy equals to this. And this is just 2 times the real part of z0 is the 2 times the real part of z1. Okay, so, well, I should better get rid of these two. Okay, so, okay, all right. So let me summarize what you have done so far. So we have these two complex numbers, z0 and z1, and they have the same moduli, and those two guys have the same real part. So this just leaves us just two possibilities. The possibility number 1 is the z1 and z0, they must be the same number, same complex numbers. Or z0 and z1, they are two different complex numbers, but they are sharing the same real part. In other words, z1 and z0, they must be complex conjugate to each other. But the first assumption must be impossible. So if z0 is z1, then what do you have? So when z0 equals to z1, then these two guys, they both cancel each other. So therefore, effectively, so this linear fractional transformation turns out to be just a constant function, so which is not true. Therefore, So since this guy never be the same as Z1, so Z0 must be the complex conjugate of Z1. Sorry, yeah, I should better say, sorry, I changed my mind. So Z1 is the complex conjugate of Z0. So this means W is e to the I times alpha over Z plus, what was it? Yeah, Z0 and Z plus Z0 bar. And okay, great. Oh, okay, good. Well, yeah. Although this final expression is slightly different from this expression, but it's minus, and you can always change the sign here. So yeah, I think this effect, this actually proves that state. Okay, all right. Now, for the other side of statement, this time around, I am supposed to prove that if my linear fractional, if my linear fractional transformation looks like this, then I must show that then this map is actually mapping this upper half plane onto this unit circle in W plane. Why? Why is that? Okay, so this time, so we let the yeah, just to get the consistency. So yeah, I'm gonna please allow me to change the sign. Okay, so and we suppose that the imaginary of the complex number z is greater than or equal to 0. Now, we are going to consider the modulus of this number. And if you take the modulus of this fraction, then this is just simply z minus z0 over z minus okay. All right, so let me try to consider this. So this is my complex plane. And say that this is my point z0, and this is my z0 conjugate. And well, suppose that my point z lies on exactly on this real x-axis, real line, the x-axis. Then, so well, when you measure the distance between these two, since they are the complex conjugate to each other, then those two guys have the same lengths. So therefore, if z is a point on the real plane, so real line, then the ratio between these two guys equals to 1. Therefore, the modulus of this number equals to 1, right? Okay, now what? Now suppose that my z is on this upper half plane. Then if you measure the distances between these two, so if this is my z, then this is, well, okay, so this is 1. This is, well, comparing the lengths between these two, this guy is clearly shorter than this distance. Therefore, the modulus, the moduli of W, modulus of W must be less than 1, right? Yep. All right. The next example is this. Hold on. Actually, no. Well, so sorry. Please allow me to go back to the previous discussion. So I said the length between the length of this guy is shorter than the length of this guy, but this is only true when the imaginary part of my point z0 is greater than 0, right? Well, suppose that what if my z0 lies on this fourth quadrant? Then in this case, conjugate of z should be in the first quadrant. Then in that case, the ratio between, well, in this case, the ratio between these two guys must be greater than 1. Okay, so there, which implies this Cayley, so this linear fractional transformations, so-called the Cayley transformation, well, actually maps the real line into the unit circle, but depending on the location of this point, sometimes this guy maps the upper half plane to the interior of the unit circle, or sometimes upper half plane to the exterior of the unit circle. Okay, so that depends on the choice of z0. Okay, all right. Okay, so let me try to consider this guy. So interestingly, so well, this example actually has, so these four coefficients, A, B, C, D, and A, B, C, D, they all turns out to be real numbers, not complex numbers. Well, if your coefficient of the linear fractional transformations are all reals, then very interesting thing happens. To another upper half plane. Okay, so why is that? So in order to justify the statement, so we will need to compare the imaginary part of the W and the W and Z. So what is the imaginary part of this guy? So this is the same as the imaginary of this complex fraction. And in order to get the imaginary part, so I will need to multiply the complex conjugate of the denominator to the top and bottom. So z minus 1 times z bar plus 1. And so this is z squared plus z minus z bar and minus 1. Everything by z plus 1 squared. Okay. Well, as always, z is x plus I times y. So since we are only looking for the imaginary part of this complex number, so this is always real number, right? And this is also real number. So these two guys are out of consideration. And so, so if I add z minus complex conjugate of z, complex conjugate of z, then this is going to be well, maybe 2 times y over okay. Great. So what does it tell us? It tells us if my complex number z has the is on the boundary of this upper half plane. In other words, if y equals to 0, then the imaginary part of W also must have the 0 imaginary part, right? So therefore, this guy is actually maps the real line in the W plane, sorry, real line in Z plane into the real line in W plane, right? On top of that, suppose that this Y has the positive sign. So suppose that Y is a positive real number. So in other words, suppose if my Z is in the upper half plane of the Z plane, then the image of this point, and the imaginary part of the image of this point also must have the positive imaginary, right? So which implies the upper half plane is being mapped to another upper half plane. Okay. So and actually this is a very interesting observation. Suppose that you have a linear fractional transformation. Maps the upper half plane to the upper half plane if and only if these four coefficients if these four numbers are all real numbers. I guess you can easily prove this. Well, just by using the same tree. If you consider the imaginary part of the complex number W, then you can easily verify this thing. Okay. So we have studied two very special linear fractional transformations. The first one is actually mapping the upper half plane to the unicircle, and the another one is mapping the upper half plane to the another upper half plane, and the last one is a linear fractional transformations which map the unicircle to the unicircle. Well, obviously the identity transformation always to satisfy the condition, but we are still trying to find, well, non-identity linear fractional transformation which maps the unicircle to the unicircle. Number 3 goes like this. I have a linear fractional transformation that looks like this. And we are assuming that this guy maps the unicircle the unicircle. Then in this case, I must be able to write down this linear fractional transformation in this form. AZ plus B and BZ plus A bar. So the patterns of these four numbers are interesting. So this number and that number, they are complex conjugate to each other. And this number, that number, they are also complex conjugate to each other. And times some rotation factor, rotation by degree theta, theta radians. So it tells us that every such a linear fractional transformation can be written in this form. Okay. All right. So why? well, since this guy maps the unit circle to the unit circle, therefore, if I plug in any complex number whose moduli equals to 1, then the resulting number, W, also must have a modulus 1. So must be 1. Okay. And I want to rephrase this the second condition. So AZ plus B is CZ plus D. Well, and this equality is still true even if I raise the power of 2. So AZ plus B and complex conjugate AZ plus B bar is CZ plus D times C bar, Z bar, and D bar. So, and now I want to expand these expressions. So A squared times Z squared. Well, but, oh, hold on. But since we are assuming that the modulus of Z equals to 1, so yeah, please allow me to get rid of this. Plus A, B bar, and Z plus A bar, B, and Z bar plus B squared is, well, the same. C squared plus C D bar Z plus C bar D Z bar plus D squared. Okay, so getting a little bit complicated, but still doable. So, well, so you must be able to recognize that these two guys are complex conjugate to each other, right? So adding two complex conjugate numbers, so it is just nothing but the real part of this number and C squared and D squared plus 2 times the real part of C, D bar, and Z, I guess. Okay, all right. So this condition is true for all such complex number Z. All right. Okay, so now I need to plug in I need to pick some very clever choice of Z that makes some very, which gives us very convenient conditions for the 4 complex numbers A, B, and C, and D. I think, so well, I should better plug in Z equals to +1 and Z equals to -1 and Z equals to I. Okay. So we let if Z equals to 1, and this condition actually reduces to A squared B squared plus 2 times and C squared and D squared and 2 times of CD bar. And if I plug in Z equals to -1, then I will get almost identical relations. But since I supposed to have the negative signs, oh, sorry. I am supposed to have the negative signs here and there, right? But, well, if I have negative signs here, then this negative sign can be taken out of this real part. Okay. Okay, good. Finally, let me say Z equals to I. Then well, I need to put one additional tiny little imaginary unit I here and there. In this case, well, the real part of this I times this guy is, well, yeah, this always confuses me, but well, this is just minus of imaginary part of this, right? And minus of 2 times the imaginary part of CD. Okay. All right, good. Now what? Oh, well, without too much trouble, yeah, I can actually derive some very interesting identity from first two equations. If you add these two equations, then this guy, and this guy, they both cancel each other. So it turns out a squared plus b squared equals to c squared plus d squared. Okay. So a squared plus b squared is c squared and d squared. And since these two guys are the same numbers, so well, we can also safely get rid of these four terms from these equations. So also we can say that real part of AB bar is real part of CD bar. And I get the same relation from the last equation. So since these numbers are the same thing, so eventually the imaginary part of these numbers also must be the same. Okay. Oh, so I have two numbers, A times B bar and C times D bar, and they both have the same real and imaginary part. So they are the same complex numbers. AB bar is C times D bar. So, well, in other words, A over C is D over B bar. Yeah, so I should better say everything taken complex conjugate. Okay, all right, we are not out of wood yet. So I will let C equals to, I'm going to simplify this relation a little bit more. So I will let C equals to lambda times B bar. Well, because, so they must have some ratios. So, you must be able to find such a number lambda. Then, so if I plug in C equals to lambda times B bar, then you can actually safely get rid of the B bar. So A must be the lambda times D bar. So A is lambda times B bar. So, and I want to plug in this relation, this guy into here and this guy into there. So, and since we are talking about the modulus, so lambda squared and the modulus of d squared is d bar squared is, it's the same as the d squared and b squared and c was and c bar squared and b squared and b squared. So combining the like terms, so d squared minus b squared is d squared and minus b squared. So we have two possibilities. D squared must be the same as b squared, or lambda squared equals to 1. Well, suppose that d squared equals to b squared. Then now what? Then, so I'm going to show you that this is impossible. Well, if d squared equals to b squared, then you're going to get some contradiction. I will show you how. Because if this guy equals to this, then this guy equals to that. So therefore, a squared is the c squared. Okay, so that means b and d and a and c, they have the same moduli. So you must be able to find some common real number, alpha. So b is this guy times D, and A is e to the I beta times C. Of course, alpha and beta, they are real numbers. So A over C is e to the I beta, and D over B is e to the minus I times alpha, and taking complex conjugate, so e to the I alpha, right? Okay. Now, all the way through, so okay. Now, I want you to take a look at this relation. This number is the same as this number. So it turns out this number equals this. E to the I alpha is the same as e to the I beta, right? Okay, now what? So e to the I alpha is e to the I beta. Then is it a contradiction? Oh, yes, because then AD minus BC is in this case, well, so A is this guy times C, and B is this guy times D. Oh, then this guy equals to 0, right? So which is contradiction. You have to remember, so in order to be a linear fractional transformation, then AD minus BC must be always non-zero. And clearly, this fails to satisfy this condition, so which implies that this is impossible. So B squared is never be the B squared. So therefore, lambda, the modulus of the lambda is 1. So we say lambda is e to the I theta. And clearly, theta is a real number. Okay, great. Where are we now? So AZ plus B over CZ plus D is, what was my A then? A was, okay, so lambda times D bar. So lambda times D bar of Z plus, what was my B then? Oh, yeah. I'm getting confused. So B is okay, so, well, yeah, sorry. C was lambda B bar, so, and C was lambda times B bar. So this means B is lambda inverse C and taken conjugate. So this is, lambda inverse of complex conjugate times C bar and CZ plus D. Okay. Okay, hold on. But what is my lambda? Lambda was e to the I times theta. And if you were taking the inverse of this guy, it's going to be e to the minus I times theta. And now you take a complex conjugate, then this is still going to be, this is going to be just lambda itself. So lambda times d bar z plus c bar over cz plus d. So which is just e to the I theta times and cz plus d. Yeah, I think my proof is done. Why? Because, yeah, it was a long way, but well, so these two numbers, they are both complex conjugate to each other, and these two numbers, they also complex conjugate to each other. And this last equation is actually these numbers are complex conjugate, and these two numbers are also complex conjugate, multiplied by some complex number whose modulus equals to. Okay. All right, great. Yeah. Well, so just a few additional remark, which is cherry on top. Well, if you have another textbook, then sometimes they say, so therefore this equation actually characterizes every linear fractional transformation that maps a unicircle to the unicircle. But in other textbooks, they will sometimes show you some different form of such a linear fractional transformations. And from time to time, you can actually rephrase these linear fractional transformations like this. This is a linear fractional transformation that maps circles to unicircle to the circle. Okay, but these numbers, yeah, I'm always free to change the sign, so allow me to change the sign from positive to plus to the minus. Then e to the I theta, and we divide this fraction, top and bottom, by d. So minus cz plus d. So e to the I theta of d bar of d z minus d of c bar and minus d of c z plus 1. Okay. Well, this number, so d bar has been divided by d. So clearly this complex number has modulus 1. So we let e to the I theta 0 is d bar over d. Then e to the I theta times e to the I theta 0 and z minus c over d times d bar and minus c d z plus 1. And these two numbers, they cancel each other. So this is simply c over d, everything taken complex conjugate. So, so I'll just simply say this is E alpha. Combining these two numbers, I'll just simply rename it by e to the I times alpha. And z minus z0. And I will put just this guy equals to z0. Then z minus and 1 minus z0 times this. Okay, good. And I prefer this expression more than that expression because if you take a close look of this last expression, then actually it gives us the idea of which point is being mapped to the origin in W plane. So, in other words, so suppose that you plug in z equals to z0. If you plug in z equals to z0, then this function value must be obviously equals to 0, right? So that means if your point z0 is inside of this unicircle, so if z0 is inside of this unicircle, then it turns out this point is being mapped to the center of this unicircle in W plane. So it actually gives us the idea that the whole interior of this guy is being mapped to the interior of this one. Okay. But however, suppose if this guy is outside of this unicircle, then what? In this case, then this inside, then Okay, so outside is inside, then in this case, the inside of the unit circle is being mapped to the outside of the unit in W. So it gives a slightly better idea. All right. Okay, good. And okay, so now today we are going to talk about some other functions other than the linear fractional transformations. So we have also very many interesting analytic functions, such as the logarithmic functions and exponential functions and the polynomials, or sine and cosine functions. Well, I do not talk about the log functions and exponential functions. They are very easy to characterize because, you know, log functions. So, well, speaking of log functions, first you will need to specify the branch of your log function. But here I am choosing the principal branch of the function. So I times the data and the is from 0 to 2 pi. So this is what? So this actually maps all real or every complex number, every non-zero complex number to the infinite strip. Infinite horizontal strip lies between 0 and 2 pi. Okay. Okay. What about the exponential functions? Exponential functions is also easy. So if e to the z is e to the x plus I times y, then this is also easy. So this maps every rectangular region to some radial region. Yes, I don't want to talk about that anymore. And the interesting one is the trig functions. So now I want to discuss the image of some geometric objects in Z plane into the W plane. So in order to discuss that, I will need to divide this guy into, break down this guy into the real part and the imaginary part. And what is the definition of the sine functions? So sine 2 times I, so e to the iz minus e to the minus iz, right? So this is our definition of the sine function. And since the z is always x plus I times y, so 2I and I times minus e to the minus I times x plus iy. Okay. I'm going to leave it as an exercise. Actually, I think we already did this one. And it turns out this is hyperbolic cosine of y plus I times cosine x times hyperbolic sine of y. Okay. Oh, so you might consider this function as a map from two-dimensional Euclidean space to another two-dimensional Euclidean space, such that the x and y is being mapped to sine x hyperbolic cosine of y and cosine x times hyperbolic sine of y. Okay. Okay, so what is the image of any rectangular region in xy plane? So for that discussion, so we will need to consider the image of any vertical line and image of any horizontal line. So suppose that I have a vertical line of a say x equals to x0, then u is what? So sine x0 and cosine, hyperbolic cosine y, and v is cosine of x0 times hyperbolic sine of y. Okay, so so this is a real number, and since we are talking about some periodic functions, sine x0 and sine y, cosine y, cosine x0, so we should better restrict ourselves between minus pi over 2 and plus pi over 2. Okay, so what do you think is the image? So y is a just parameter, free variable, and cosine x0 and sine x0, I will somehow need to get rid of this dependency of x0. So therefore, what? Yeah. So since sine square plus cosine square equals to sorry, I messed up. Oh, okay, yeah. So sorry. I need to get rid of the dependency of free variable y. Then, since hyperbolic cosine squared minus hyperbolic sine squared equals to 1, so u over sine x0 squared minus v0 squared over cosine square of x0 should be 1. Okay. Can you recognize this quadratic polynomial? Well, this quadratic polynomial actually represents a hyperbola in UV plane, right? So, which looks like this. What is the coordinate of foci? Focus of this one. So focus is, well, the focus, the coordinate of focus squared is always this guy squared that guy, this guy squared this one. So, focus is always 1, independent from the choice of x0, right? So this is minus 1, and this is plus 1, and I must be something more like this, okay? Okay, and if x0 moves between this interval, and in particular, if my x0 equals to 0, then this is going to be nothing but, well, if x0 equals to 0, then this guy is 0, and well, then this is 1. So therefore, then in this case, the image of this guy should be just a single line on the y-axis, right? Okay, but something is not right, because, well, the image was since we are talking about the image of this vertical line, therefore, well, actually, I should say, well, just one side of, so not these two, well, we have two connected components of two curves, right? And one of these two components must be the image, not both of them, right? Well, suppose that x0 is positive. If x0 is positive, then this is positive and this is also positive. So therefore, so if x0 is positive, then this guy is going to be the curve, image curve. And if x0 is negative, then this guy must be the image, right? Well, although we are talking about when x0 is moving between these two, but because of the periodicity of the sine and cosine functions, but this pattern actually continues for every x0 in for all real numbers, for all every real number x is 0. Okay, and also I want to talk about two extremes. So if x is 0, if x is 0 equals to 0, then the image curve is going to be nothing but the y-axis of the W plane. What if my x0 equals to precisely pi over 2? If my x0 is precisely pi over 2, then v coordinate equals to 0, and sine of x0 is going to be 1, right? And in this case, for every real number y, hyperbolic cosine is always greater than or equals to 1, right? So that means, well, the image curve is going to be this line sigma. Well, on the other hand, if x0 equals to minus pi over 2, then the almost the same thing, but the image curve is going to be a half line, so starting from this point and to the minus infinity. Okay, so this is about the image of the vertical line. Now we need to talk about the image of a horizontal line. Y is y0. Then in this case, so it's y0 and y0. Then also, well, sine square plus cosine square is 1. So u square of hyperbolic cosine of y0 plus v0 over hyperbolic sine squared is 1. And can you recognize this quadratic equation? Yeah. Well, the first one, this guy was an hyperbola. And therefore, since we have the sign of this guy, the sign of this guy is positive. So therefore, the image of this one should be an ellipse. What is the focus of this guy? Well, the focus of this guy turns out to be, hyperbolic cosine is always greater than the hyperbolic sine. So therefore, this guy squared minus that guy squared is 1. Oh, right. The coordinate of focus is still -1 and +1. Okay. So this is going to be the image of your. So this is the image of your curve, horizontal line, and well, if y is y0, and so this is a periodic curve, right? So the image of x, y is x is between minus pi to plus pi, and y is y0. Okay. All right. Okay. Now, also, I want to consider two extremes. What if y0 equals to 0? So if y0 equals to 0, then this guy is 0, but this guy is 1. Therefore, the v coordinate vanishes, and the u coordinate is going to be a number between -1 to +1. So now I get it. So as y0 increases, then your image curve is more and more like a circle, right? But on the other extreme, if y0 is getting really close to the 0, then your ellipse is like shrinking and shrinking and shrinking and shrinking, and eventually we'll be converging to a line segment between minus and plus. All right. Okay. Okay. Minus pi plus pi, and okay. This is not that horribly complicated, but sometimes, well, confusing. So just to make sure we are on the right track. So we need to consider, I want to consider the image of this so this rectangle. So this is minus pi to plus pi, as minus pi over 2 plus pi over 2. And this from 0 to b. What do you think is the image of this guy? Well, so I said if as x0 is somewhere between this interval, then the image curve is going to be, well, the image of, well, as x0 moves between these intervals, then the image of this guy must be some, well, the entire area between these two hyperbolas, right? But if my x0 is precisely plus or minus pi over 2, then that is going to be the line segment from starting from here then to there, and from starting from here to the over there. So yeah. So yeah, I know this is the right picture, but well. Looks like this. So well, and so everything above this here gonna be the image when your x is between this and that. And well, also when b, so y equals to 0, then you're gonna get a line segment from here to there, right? So this is the one extreme of this ellipse. And when y is equals to b, then you're gonna get some curve like this. Okay. Okay. Am I right? So yeah, maybe, probably. This is huge maybe, but I should better color all this guy. Okay. Well, in general, so roughly speaking, so the complex sine function is actually mapping this interval into usually your complex sine function is mapping every rectangular region into some this oddly shaped region in W plane. Okay, all right. Okay, yeah, I have spent too much time just explaining about the sine functions, but you know, there are still many other interesting functions. Like for instance, we will still need to discuss about the complex cosine and hyperbolic cosine and hyperbolic sines and so on. So there are so many things to discuss, but there is always an easier way around. Well, first, complex cosine function is sine z plus pi over 2. So therefore, this guy can be considered as composition of these two functions. You just parallel translate this guy by pi over 2, and then you take the sine function. So, well, therefore, cosine function is nothing but some parallel translation of the complex sine function. And on the other hand, hyperbolic sine function is e to the z minus e to the minus of z divided by 2. So this is maybe minus I times sine of I of z. Okay, yeah. So, so this one can be also understood as rotation by 90 degrees. And you take complex sine function. And finally, you rotate by minus 90 degrees. Okay. So you can still you can still understand how complex hyperbolic sine and composition of these three functions. And finally, so hyperbolic cosh is this. So well, suppose, well, provided that you already understood, okay, complex cosine function, and complex hyperbolic cosine is nothing but rotation by 90 degrees and composed by hyperbolic complex cosine. So technically, so this is how you understand all these functions. Okay, all right. Well, today, I think this is the right time to finish today's lecture. Yeah. Sorry, yeah. Yeah, I took too much time on just pure tedious computations, but well, sometimes sometimes you need to spend some time in tedious computation. This is how you run mathematics, right? All right. Thank you for your patience and see you next time.